Okay, so acids and bases. So this is something that a lot of times people like to go, oh, acids and bases, that's all chemistry. But the pH of things, which is your percent hydrogen, measuring whether or not something is an acid or base, is also really important in biological concepts. A lot of times in a cell or an organism, it's going to turn things on and off. And so that's a pretty big deal. What's going to control your rate of breathing is going to be largely controlled by your pH. So if you become more acidic, your body's going to want to breathe faster to try and change that in there. So the hydrogen ion, when you have water split, you can't split it equally in the center. So there's no splitting that in half, because if you split that oxygen in half, it's no longer oxygen. So remember, this bond represents that there are two shared electrons here. So the oxygen has to go with one of the hydrogens, and these two are much more electronegative than the hydrogen alone. So when they sever this relationship, they aren't going to take what they come into it with. The bigger party gets everything in the deal. So what you're left with is the hydroxide that ends up with an extra electron. It will have a negative charge. And the hydrogen ion, which has given up its electron then and has a positive charge in there. So sometimes you'll see it written as the hydronium in there, where it becomes, it doesn't like to actually hang around by itself, so sometimes it will attach onto a water like that. Just be aware that you may see that in there, but for abbreviations in biology, we will usually just use hydrogen ion in there. So it's a reversible reaction between these being separated and being together as water. So you're going to have an equilibrium in there of how much is separated and how much is together that will constantly be separating and coming together, but once they reach equilibrium, it's done at an equal rate in there. So in pure water, there is one molecule molecule in every 554 million that is dissociated in there. So somebody calculated that out for us. And when you look at that, the concentration of each ion in pure water is 10 to the negative 7th molarity at 25 degrees Celsius, which is a pH of 7. Good news, you're not going to have to worry about calculating any of that in there. There are ways to calculate the pH of different things, knowing the different concentrations of it, and I can honestly tell you I have never had to use that outside of a chemistry class in there. So I'm not worried about you being able to do the calculation. So with our pH scale, it's going to go from 0 to 14. The 0 to 7 end is going to be the acidic end. So the smaller the number, the more acidic it is, and it means the concentration of the hydrogen ion is greater in there. If you go the other direction, over here, it means that the hydroxide ion is more concentrated in there, and it becomes increasingly basic as you move away in the other direction. So right in the middle, at 7, is going to be pure water. So when you move away towards smaller numbers, more acidic, towards bigger numbers is more basic in there. A lot of times people look and they go, well, okay, the acids are bad and dangerous in there, that's going to be a problem. It's not that any of them are good or bad. They are appropriate in the appropriate place. If you stick the wrong pH in the wrong place in the body, it can cause damage in there. So different things have different pHs. Your blood and your tears are a little over a pH of 7 in there. And so for those substances, that's good. Your urine is around a pH of 5. So if you had your urine get up here towards this, you would be just prone to urinary tract infections right and left in there. So the more acidic is actually good in that situation in there. Your stomach acid is about a pH of 2 in there. Now, if you had that flowing through your blood, not good. But in your stomach, it's actually essential for you to be able to digest food. So different pHs are appropriate at different spots in there. A lot of times people will get really alarmed and, if somebody hands you a battery that's cracked open and you see the battery acid on it, most people are like, get it away from me. You take it over to the garbage can where you want to wear gloves or something like that, or carry it with tongs. Everybody gets really freaked out about touching it in there. And yet if you get lemon juice on your hands or vomit from your gastric juices, it's a similar pH in there. So those kind of things, if you got lemon juice on your car or if you put soda on your car, it will damage the paint. If you throw up on your car and you don't wash it off, it will damage the paint in there. And people don't react to those things nearly like they do to battery acid. You willingly open your mouth and pour this stuff in there. Most people eat vinegar in something or other. Most salad dressings are going to contain vinegar in there, and nobody thinks anything about that. So we have this perception of acids being bad. Now, if your skin can be damaged by a strong acid, yes. It can also be damaged by a strong base. If you left it on there for a long time, it would take a long time for that battery acid to actually cause a problem for you too. Because if you've kind of been, if you have to deal with kids and stuff like that and there's the batteries in there, you don't want them doing it, so you just go, whatever. I will suck it up and grab the battery that's got the acid on it, and you're like, I still got it on my fingers. Didn't really do anything to me. You realize some of those things were just stuff you heard growing up in there with the damage. But, something like leaving bleach on your skin could actually cause more damage than that battery acid's going to in most cases in there. So the pH, it's about the things being the correct pH in the correct location, not whether they're good or bad in there. Usually the more towards the end something is, the more reactive it is in there. So your bleach, which is going to have high amounts of chlorine in there, very reactive because it really wants to gain that extra electron in there. So more reactive at the ends of the spectrum in there. So when an acid dissolves in water, it's going to donate a hydrogen ion in there, and it increases the concentration of it. So what happens is a substance gets mixed into the water that will let go of its hydrogen ion, and that's what makes the acid solution in there. So with hydrochloric acid, what happens in there is you've got hydrogen chloride here, and the chlorine separates and it donates this hydrogen ion. So for a base in there, it's going to reduce the amount of hydrogen ion in the solution in there. So an example would be with ammonia in there and it pulling up that extra hydrogen ion. Or it can indirectly do it with looking at the hydroxide ions too. There's two ways of defining it. Sometimes people will define it with the hydroxide ion. Sometimes they define it with the acids in there. Either way is correct in there of doing it. Chemistry's just they're as bad as biology for having more than one way of doing some things and coming up with extra names in there. So when we talk about something being a weak acid or a weak base, these are going to be ones that are going to bind and release reversibly in there, where a strong acid or a strong base, they will completely dissociate. So the way we would indicate that in a chemical reaction is the strong acids or bases in a reaction we use a one-way arrow. The other ones, the weak ones, we use a reversible arrow in there. So with the pH scale in there, it is considered to be in an aqueous solution at 25 degrees Celsius, which is a nice, warm, comfortable room temperature in there. So I'll show you the math that's behind it here and there so that you have an idea of where this information comes from, but I am not going to ask you to do this math. So you've got your concentration, which is what the brackets indicate here, concentration of hydrogen ions and hydroxide ions. And in normal water, it's at a constant at 10 to the negative 14 in there. In a neutral solution in there, it means you've got 10 to the negative 7 that is the hydroxide ion, 10 to the negative 7 that's the hydrogen ion in there. So when you multiply them together, that's where the 10 to the negative 14 comes from in there. So if you have an acid and it's going to increase the hydrogen ion concentration to 10 to the negative 5th. So remember, when the negative number's up here, it's the decimal in there. So what you've done is you've moved it closer to the decimal point. So that's actually a bigger number with the smaller negative number on the top on there. Then the hydroxide ion has to shift the other direction in there. And so it maintains that 10 to the negative 14 in there. So the way that you can actually calculate the pH of a solution is you use the negative log to the base 10 of the hydrogen ion. So what that means, if you're looking at that math equation and going, oh, I remember hearing that log word and I ran from it when I took math, it means it's a tenfold change. So each time you change a whole number on the pH scale, it's actually a tenfold change. So that's what all of that mathematical equation is telling you in there, numerically is. So the difference between a pH 2 and a pH 3, pH 2 is 10 times more acidic than a pH 3. pH 1 is 10 times more acidic than a pH 2 in there. So it actually kind of increases logarithmically as you go out. And that's why the ones at the end of the scale are much stronger and much more reactive in there. Yeah, so that log, when you see a 14, it's going to be a negative log of 10 to the negative 14. So it's a negative times a negative in there. It becomes positive because you do negative times negative in there. So the pHs are never a negative number. It's just in the log of doing the math for it that it is. Like I said, I have never had to calculate the pH of anything outside of a chemistry class. And so I'm not going to make you do something like that the last chemistry class I took was in the 90s. I feel pretty safe in saying I don't think you're going to have to calculate the pH of anything in healthcare like that for anything serious coming up. So buffers, these are going to be substances that minimize the change in a pH. So if the pH change is going to turn things on and off, you don't really want that to be too touchy and that switch going on and off too easily. So if you've ever had like a light switch that starts to get kind of worn out in there, or like when your sliding glass door thing gets worn out and you go to unlock it and it just falls down locked, that's really a bad thing. You should change that. I got locked out of a house twice in one day from a lock that was that way. I was mad the second time. Because what had happened is the dog would just pat it and that'd go down. And then he'd sit there and bark at me and laugh. And I'm like, oh. So you don't want that going on in your body where things change too easily like that. So what a buffer does is it's going to help absorb some of that pH change so that you're not going around. This allows you to maintain a relatively constant breathing rate. Otherwise, as soon as you stood up, you'd be like trying to catch up and then dropping back down. That way it can be soften the changes of things in there. It makes it a lot more pleasant to be a human with those in there. So it's going to accept hydrogen ions when they're in excess. It will donate them when they're depleted. Buffers usually have a specific range that they will buffer in, a pH range in there that they will do that. So different buffers will buffer different ranges in there. And so you can kind of think of it being like a kitchen sponge. When it's all dried up on the counter, it's not, and you first put it under the water, it doesn't help absorb and buffer any of the water that falls into the sink. It just all runs off there. But when it starts to get a little bit wet, it enters its buffering range where it can absorb some of that water. But at some point it will become saturated and all the water will run into the sink again. So your buffers are kind of like that, where they've got just that little zone in there that they'll work with. So threats to water quality on Earth: acid precipitation with rain, snow. It's defined as rain, snow, or fog that has a pH less than 5.2 on there. And different sources will say that the pH of different things is at different places. One of the things you're going to be doing in here is you'll be measuring some pHs. And if you want to measure some sort of body of water that's by you, I wouldn't mess with a river. They'd change too much with flow of glaciers that end up in there. But if there's a lake or a pond somewhere close to where you live that you wonder, is this really acidic in there, you're welcome to bring in some of the water for that lab that we do coming up so you can test the pH of the things in there. All we have in here are pH strips. I thought I found a pH meter that somebody else used the lab and left around, and if that's the case, we'll use the electronic one. The one I ordered, they didn't send the probe. They sent the computer part and not the probe. I will try and figure that out for you. I got to look and see exactly which lab it is in there. But they say most of the lakes are around a pH 4 to 5. What we've measured from rain that's collected here on this campus and other classes, it wasn't that bad. So I find it hard to believe that Tacoma is really exempt from some of the effects of pollution, but it could be different days we catch different amounts too. Yeah. Well, it should be pure water, but the more pollution you have in the air, what happens is those pollutants interact with the moisture in the air, and what comes down is acidic in there. As it becomes more acidic, it sustains life less effectively. Also in the oceans, it will start to dissolve corals, because anything with calcium in there will start to dissolve in a more acidic environment. And they've actually been able to study that where there are volcanoes in the ocean that will alter the pH in that area, and they'll see down current from them that the coral will be in just horrible condition in there. So that's the ideal pH. It's hard to say because there weren't any of us here when it was probably an ideal pH, and we all leave some sort of impact on it in there. But different things will thrive at different pHs in there. Did you have a... Okay. So the carbon dioxide absorbed by oceans reacts with the seawater. It makes carbonic acid in there. Corals are a big one that you can see pretty obvious effects on. There's a lot of videos on YouTube. There's some on PBS out there too that I've seen on the corals in there. One of the things I want to go to and see before it gets too destroyed is the Great Barrier Reef. So I'm always looking at things like, I'm like, how many years do I have to get there before that's gone? And I want to see a glacier on Kilimanjaro before it's gone. So I guess I better be saving some money to be going some places. So if you're interested in those things, I can search for some videos and send you links on it. Just send me an email if you want them in there.